Okay, good day. This is AP Calculus. I am Mr. McCully, and this is the presentation for section 3.3, increasing and decreasing functions. Let's get right to it. Okay, so today we are going to determine the intervals on which a function is increasing and or decreasing, and then we are going to apply the first derivative test to determine the nature of a relative extrema of some sort of or some function. Now, again, this is an application of the derivative, and in the quote-unquote real world, certainly we want to know when a function is going up and or when it is going down from left to right. So let's move on here. So the first derivative test defined increasing and or decreasing functions. So if f is a function that is continuous on a closed interval and differentiable on the open interval, if f prime is greater than 0 for all x in that open interval a to b, then f is increasing on that a to b. And then if f of x is less than 0 or negative for all x in that interval a to b, then it is decreasing on the closed interval a to b. And then if f prime, I hope I said that right now that I'm thinking about it, it's not f of x, it's f prime. So if the first derivative is positive, if the first derivative is negative, or if the first derivative is 0 for all of those, then f is a constant on a to b. And so there are some formal definitions of those things on page 179 in the text that you might want to take a gander at when you're doing the practice work. So what does that mean to us as far as visually? Certainly it always helps to have a visual representation of those word definitions there. So the first derivative we know determines the slope of a tangent line at a point. So if the first derivative is positive, then the tangent line is increasing from left to right. So let's just say, as a for instance, I have a function that looks like this. All right. If I were to find the slope of the tangent line here, it would be, well, I didn't do a very good job, so let's see if I can make this go up a little bit better. There's a little bit better of a tangent line. Certainly, this function is decreasing, but the slope of this line would absolutely be a negative value. So in fact, even though if I were to find a tangent line right here at this point, say something that looked like that, all right, we may do just a little bit better job. All right, that tangent line right there, the slope of that tangent line would be negative, implying that it is decreasing. And it's decreasing at all the points around there. Now the same would hold true for some function that we had that was increasing. And in fact, let's say I had something that looked a little bit like this. If I drew a tangent line right there, oh, come on, you. It's not going to let me. Oh, well. If I drew a tangent line there, it would be increasing. And so something that if we're looking at all of the possible tangent lines along this curve, certainly this point right here is where it changes from decreasing to increasing. At this point right here, we have a horizontal tangent line. So our critical numbers from the last section, these are going to become places where it changes, it could change, and I need to stress that. These are places where it could change from either decreasing to increasing, or in this case right here, that extrema is going to be a place where it changes from increasing to decreasing. All right. So the first derivative test in extrema, there's a formal definition on page 181. And I'm going to talk about a sign chart. And basically a sign chart is going to be a chart that we're going to find those critical numbers, and we're just going to put them on a number line, and we're going to decide whether or not the first derivative is either positive or negative in an interval. So just as a kind of a example here about what a sign chart can do, for us, and I want to see if I can come up with places where we get that to do exactly what I want it to do. And so I want it to be, there's an extrema, and there is an extrema. And so if we go through and we find critical numbers, so we figure out where if this is f of x, if we find out where f prime of x is equal to 0, then our critical numbers for this particular graph would absolutely be at x equal to 3, -3, and +1 right here and right here. And this is certainly places where it changes from, in this case, decreasing to increasing and increasing to decreasing. So when I say I'm going to make a sign chart, what I'm actually doing here is I am going to draw me just a little number line right here, and I'm going to put those critical numbers, so -3 and +1, those are critical numbers. And since this function is decreasing on this interval, for any value of x that is less than -3, when I plug it into f prime of x, I am going to get a negative value. And then for any value for x from -3 to +1, because the function is increasing, I'm going to get a positive value. And then for any value for x that's greater than +1, I'm going to get a negative value for the first derivative because the function is decreasing. Now, this little visual representation can be good for you to determine, or especially when you're writing it out at the end of the question, where you're going to say what intervals are increasing and or decreasing. But certainly this alone, and that's what this sentence here says, this alone is not a rigorous enough explanation when we get to the AP Calculus test. So certainly you would say at something that something like if you're in a test and they say, why is it decreasing? You would say, for all the values of x between -infinity and 3, the value of the first derivative would be negative. Therefore, that function is decreasing. Just showing this as a picture is not enough for you to conclude anything. Your grader will not use that. Now, you can write it on your paper, but certainly you would have to do something to explain it. So let's get to some examples here real quick, and we'll start with a real easy one. It says find the so given this particular function f of x equals x squared plus 6x plus 10, they want you to find the critical numbers, and then they want you to find the open intervals on which the function is increasing or decreasing, and then they want you to apply the first derivative test to determine the extrema. Now I know something about this. We've done functions that look like this since Algebra 1. This is a parabola. It opens up because the leading coefficient is positive, and it goes through 10. Now, I'm not 100% sure if this has a 0 or not. I could use the quadratic formula on that to find it, but we're not really concerned about that. All we really want to talk about is we want to find the critical numbers. That's the first part. Then we want to find those open intervals on which it is increasing or decreasing. Now, the critical numbers determine the places where these intervals are. They're the endpoints of the intervals. So if I take the first derivative, and I picked a real easy one to start here, I'm going to get 2x plus 6. And when I set this equal to 0, 2x plus 6 equal to 0, I get x equaling to -3. So -3 is the only critical number. All right. Now, when I'm thinking about this thing, okay, and we know what this looks like, but there may be times when there are functions that we don't know. But off in the back of my head, I already know that this has to go through 10, and it probably does something like this. Oops, let's be smarter. This is negative, this is 10, and it probably looks something like this. 10, and this right here is -3. because we know that this parabola opens up, we know that it's going to be decreasing when values of x are less than -3. And we know that these values are going to be increasing when the values of x are greater than -3. But we want to use, and again, I'm using this simple example to describe this function, but we want to use this to prove that that's true. So we want to talk about this first derivative and using the first derivative test. And so what I can do is I can say, all right, here's my number line. I've got n points of that number line, and I only have one critical number, and that's at -3. Well, if I pick a point and just arbitrarily I call it -6, and I plug it into this first derivative, well, 2 times -6 plus 6, I'm going to get -12 plus 6 is going to be -6. So on this interval, all of these values are going to be negative. And that makes sense because this function is decreasing until we get to -3. When I plug in, say, 0, that's a value on the other side. If I plug in 0, 0 squared is 0, plus 6 times 0 is 0, plus 10 is a positive solution. So I've got a positive solution in this particular interval. And that makes sense because, again, the function is increasing on that interval, so all values of the first derivative would have to be positive. So I've got two intervals, so my answer to part A, my critical numbers, in this case, just x equals -3. B, I have one interval in which it's decreasing. It is decreasing on, let's see here, -infinity to -3, and it is increasing on -3 to +infinity. Now, what is this -3? Obviously, part C, I have -3, but I want to find the point for that. So -3, let's make a point out of it. -3 squared is 9. -3 times 6 is -18. -18 and 9 is -9, plus 10 is +1. So this point here is -3, +1. And we clearly can see that that thing, just based on what we already know about parabolas, that this thing is going to be a relative minimum. In fact, it's going to be an absolute minimum. But the reason that we know it is because this value goes from decreasing to increasing. Whenever you come across a point that changes from decreasing to increasing, you know that it's going down and then going back up. So this thing has to be a relative minimum. If the reverse is true, and I'll show you one of those in the next example, it would be a relative maximum. My next one, oh, I don't have the function. Oh no, I'll have to write it. That's no big deal. So example, this is still on the same page, it's number 44. It says, consider the function on just the interval 0 to 2 pi. Find the open intervals on which the function is increasing or decreasing, and then apply the first derivative test to identify the extrema. Well, the function that they give us is f of x is equal to sine x cosine x plus 5. And we're only looking from 0 to 2 pi, which is good because this is a periodic function. And so since we know sine and cosine go up and down and up and down and up and down and repeat, there's a lot of relative minimum and relative extrema. In fact, there are an infinite number of them. But by confining it to just the unit circle, we can lower that number quite a bit. Now, I'm not actually going to graph this function, and the reason that I'm not going to do that is because I want to apply all of these tests without actually knowing what that graph looks like in this particular case. So we want to take the first derivative of that. But as it is written, this thing right here would be the product of the sine x function and the cosine x function. And that would mean I have to do the product rule, and we could eventually come up with the right answer. But there is a shortcut, and I did give you this at the beginning of the year, but here is my fundamental trigonometric identities. And we can actually do a shortcut. If you look up here, and let me see if I can zoom in just a little bit. That's a little too much. Maybe I can get over where am I at? Oops, didn't want to do that. Come on, you. Oh, shoot. Maybe I can't. You have to go back. Come on. There we go. I didn't mean to. I wanted to. Why won't it let me do that? Come on. Alright, well, we'll go as big as we can before it zooms me out. Oh, shoot. Come on. There we go. Well, anyways, I'm looking at this one right here. It says sine 2u is equal to 2 sine u cosine u. Well, I have sine u cosine u. And so this double angle formula lets me take this cosine u, or sine u cosine u, and shrink it down into just sine u. And that's going to make our lives a lot easier. So the thing is that I'm going to use sine 2u equals to 2 sine u cosine u. Well, I don't have 2 sine u cosine u. I have just 1 sine u cosine u. So here's what I'm going to do. I'm going to use a funky one. I need that 2. So I'm going to say it's 2 over 2 sine x cosine x plus 5. And then I'm going to separate this into a fraction. I'm going to say it is, let's see here, a half. No, I'm going to say it is 1/2 times 2, because 2 times a half would be the one that I need, and it's sine x cosine x plus 5. And now I can apply this rule here, and I can say that this is a half sine, and it's not a very good sign, let's try it again, half sine 2x, still plus 5. Now that makes this a little bit easier, because now f prime of x is going to be that half, and the derivative of sine is cosine, and this is the composition of the sine x function with the 2x function. So I have to do the chain rule. So if I leave my 2x alone, multiply by the derivative of what's inside, which should just be 2, and then the derivative of the plus 5 that we have right here is just 0. So the half and the 2 cancel, and I get f prime of x equals the cosine of 2x. All right, now I need to figure out where this thing is equal to 0. So I need to find out where cosine of 2x is equal to 0. So let's talk about the unit circle. Quick refresher. Cosine is the x values on the unit circle. This is 1, and this is 1, and this is -1 there. And so the cosine is going to be 0 at multiples of this point right here. So if this were cosine theta, then, or equal to, let's just say y, I suppose, for right now, or equal to 0 would be even better. Let's do that. Equal to 0. Well, theta would be equal to these multiples of pi over 2. So they would be pi over 2, it would be 3 pi over 2, and it would be 4, oops, nope, not 4. 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on and so forth. Now, you'll say, wait, Mr. McCulley, 5 pi over 2 is outside this interval, so I shouldn't have to use those. But the thing is, we're not using theta. We're actually using 2 theta. So if I had 2 theta, or 2x, might as well say it, do it right, 2x equal to pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. If I divide all of these by 2 to get x by itself, the values of x where the cosine of 2x is equal to 0, I'll get pi over 4, I'll get 3 pi over 4, I'll get 5 pi over 4, and I'll get 7 pi over 4. And all of these are in 0 to 2 pi. All right. So these are my critical numbers. So they didn't ask for the critical numbers, so I don't have to worry about it. But these are my critical numbers. All right. So A says, find the open intervals on which the function is increasing or decreasing. Well, now here I have this, and you know what? I've got a line tool. Let's use a line tool. That'll be better. All right, we want to go from 0 to 2 pi. Well, we can do that. That's not a big deal. I got right here is going to be pi over 4. Right here will be 3 pi over 4. Right here will be 5 pi over 4, and right here will be 7 pi over 4. So again, we want to figure out what's going on here. So in cosine 2x, pi over 4 times 2 is pi over 2. And remember, on the unit circle up here, this is pi over 2. So from 0 to pi over 4, the cosine will be just in this little piece of the interval here. And since it's the x values, these will all be positive. Now, if you wanted to, you could plug in like pi over 8. You could put pi over 8 in there, and you'll get pi over 4, and the cosine of pi over 4 is positive square root of 2 over 2, which will give you positive. That works also, and that's what I did in the last example, but I'm just using this visualization to help me. Now, from pi over 4 to 3 pi over 4, well, if I plug 3 pi over 4 in here for x times 2, that'll give me 3 pi over 2. So all of these points here goes from this point at pi over 2 all the way over here to 3 pi over 2. And since cosine are these x values on this entire interval, all of those x values are negative. Then from 3 pi over 4 to 5 pi over 4, well, 5 pi over 4 times 2 is 5 pi over 2, and the cosine of 5 pi over 2 is 0. So again, that's why it's a critical number. But from 3 pi over 2 up to here again gets me to 5 pi over 4. And the x values anywhere along this portion of the unit circle are positive, so it's going to be positive. And then you can guess the rest of them. I'm going to go from here down to there, that would make it negative again. And then this one will only go from here back up, which would give me some more positive values. So when I look at this thing, and again, the directions say, find the open intervals on which the function is increasing and or decreasing. Okay, so from 0 to pi over 4, since the values of the first derivative are positive, it's increasing. From pi over 4, to 3 pi over 4, because the values of the first derivative are negative, it's decreasing, and it changes, goes back and forth from all of those. So I have increasing functions. So part A, this is increasing on, I have 3 intervals. So from 0 to pi over 4, and this is 3 pi over 4 to 5 pi over 4. That's the second interval. And then the last interval is 7 pi over 4 all the way to 2 pi. It is decreasing on the values where it's negative. So 3 pi over, oops, I want to start it, just pi over 4. So pi over 4 to 3 pi over 4, because that's where it's negative, and from 5 pi over 4 to 7 pi over 4. Now, they didn't ask us to justify this. The moment they say justify it, you have to say it is increase. You have to make a sentence that says it is increasing on these intervals because the value of the first derivative inside those intervals will be positive, which makes it, or the function, increasing. Part B says, discuss whether those values are extrema, or discuss the extrema of this. Well, I've got a bunch of points, and I have a 0, comma, because it's an endpoint of it's an open interval, so I don't have 0. Sorry. Back up here, I don't have 0, so it's an open interval that doesn't technically have an endpoint. But I do have, my first one is going to be at pi over 4. And when I plug in pi over 4 into the original function, this one here, the cosine of pi, or the sine of pi over 4 is square root of 2 over 2. The cosine of pi over 4 is square root of 2 over 2. When I multiply those together, I get 2 over 4, which is a half, plus 5 is, there's 10 halves, so 11 over 2. I also have, and let's say it'll be 3 pi over 4. And when I plug it into here, 3 pi over 4 is going to be, let's see here, 3 pi over 4 will give me, the sine value be positive square root of 2 over 2. The cosine will be negative square root of 2 over 2. So that'll be negative a half plus 5, which would be 9 halves. And then I have 5 pi over 4, and again, 5 pi over 4 is going to be, let's see here, 5 pi over 4 is going to be in the third quadrant. I'd have negative square root of 2 over 2, negative square over 2 over 2, which would be positive half plus 5, and that's going to be, again, 11 over 2. So I have a feeling that this last one, that's not pi, it should be pi. Screwed that up. Let's see if I can do this. It should be 11 over 2. And then 7 pi over 4 is going to give me 9 halves. Now, we know that because this thing, our function, is increasing to the x value pi over 4, and then it's decreasing after, we know that it goes up and then it goes down with pi over 4 as its x value at that point. So this is a maximum. It is decreasing and then increasing, so this is a minimum. It is increasing and then decreasing, so this is maximum. And it is decreasing and then increasing, so this one is a minimum. I think that's it. A and B, we're good. All right, last one's an easy one, and that's good. So, example, use the graph of F to sketch the graph of F prime. And so, right here, and this is my F of X graph, and this is my F prime of X graph. And so we want to graph what the first derivative is going to look like. So I have changing from increasing to decreasing at values of 2 and a value at 0, and then another value at positive 2. So negative 2, positive 2, it changes from increasing to decreasing, and then from decreasing to increasing, and then from increasing to decreasing again. So on this function right here, this is increasing. And so the first derivative has to be positive. And since the first derivative is positive, here it's going to be increasing very quickly, and then it's going to start slowing down and becoming a lot smaller. So my first derivative starts off increasing a whole lot, and then it slows down and slows down and slows down, and then at 0, or at negative 2, there is a horizontal tangent line. So at f prime of 2, we get 0. So I graph 0. Why? Because this is the graph of the first derivative. It's 0. So this function is decreasing, and it starts decreasing, and it's decreasing really fast, and then it slows down again, and then again at f prime of 0, we get another 0. So this function has to come down, and I don't know how far it goes down, but I do know that it has to be 0 again. Now it's increasing, so any value along here, that first derivative, is going to be positive. And so, again, it's increasing. And then again here at f prime of 2, that's going to be 0 again. So I'm going to get something that's increasing, so the first derivative is positive. And then I have a horizontal tangent at x equals 2. That's when the first derivative equals 0. So since this is graphing the first derivative, f of 2 we know to be 0, so it's got to be 2, 0. And then from this point on, it is decreasing, and it's just going to keep decreasing at a faster rate. So this measures the rate at what it's doing. Since the first derivative would be negative here because it's decreasing, our first derivative graph is negative, and it's decreasing at a faster rate. We can do a couple more of these in class, but there is one thing I am going to tell you. When we get to this section, one of the work days will be a performance task, and it'll be a quiz, and you're only going to really get one chance at it. I'm going to break you up into 2 or 3 groups, I think. We got, I'm not sure how many people we have. I'm going to break you up into a few groups, and the task is going to be to take 16 pictures. It's actually 32 pictures, and one will say f of x, one will say f prime of x, and you will do something like this in your head, and you're going to match them. And it's a 16-point thing, and it's a work together task, and nothing to get too stressed over, but it's certainly fun, but certainly something you want to think about. So when you're doing these types of problems in the practice work, you certainly want to take your time and know how to do those. All right there, folks, that's all I have. And today's fun fact of the day. This is Shmi Skywalker, and she is Anakin's father, and that would make her Luke Skywalker's grandmother and Kylo Ren's great-grandmother. And so the one fun fact about her is it is at least implied in episode 1 that she gave birth to Anakin without a father. So Anakin was a virgin birth, a Christ figure. Lucas threw that in there, which I was kind of surprised at even back then. So that's all I got today, folks. Have a good one.